let's get started. Today, we are very happy to welcome our speaker, Dr. Hanshu Yan, to come to visit our Recon AI Center. Hanshu is a research scientist at TikTok, ByteDance, Singapore, who was efficient and controllable diffusion-based generative models. He obtained his PhD from National University of Singapore this year. And before his PhD, he got his master from Singapore as well, and his bachelor degree from Beihang University. Let's welcome Hanshu to give his talk today towards adversarial robustness of diffusion algorithms. Welcome. Please.
Okay, thank you. So, hello everyone. My name is Hanshu Yan, and welcome to my talk. The topic is towards adversarial robustness of diffusion algorithms. I want to thank Dr. Jinfeng Zhang and Prof. Sogi to invite me to visit Recon AIP, and so happy to come to talk here. So now I'm working as a research scientist at ByteDance Incorporation, and during PhD I did a short-term remote intern with Recon AIP, working very closely with Dr. Jinfeng Zhang and Prof. Sugiyama. My research interests include deep generative models for image and video generation and editing. And recently we have published two papers about the diffusion-based generative models to do the semantic blending for images and the video generation. Besides, I'm also interested about the adversarial robustness of machine learning algorithms and the efficient deep optimizers. So now let's begin the topic today. As we know, the intelligent system has changed our daily lives. For example, it facilitates the daily communication between friends and family, and it also helps the doctor to make diagnosis about the disease. Among these intelligent system, diffusion algorithms play critical part in it, and such as the detection or classification algorithms. But as we all know that the deep neural networks are very vulnerable against imperceptible malicious perturbations. Here is an example. And suppose we have a classification algorithms which try to classify the road sign into the correct text or the symbol. And now, if we add some noise onto malicious noise or adversarial noise into the road sign, then the result will turn to be wrong. So it will cause very critical and very disastrous consequences if we use the system, use the algorithms in some high-stake applications. So this talk we are interested about how can we evaluate and robustify the diffusion algorithms. Here we are interested about the image denoising and the classification algorithms. And besides the evaluation and the robustification, we also interested about what can robustness bring us beyond itself, because robustification of deep networks always costs very high computational costs. So we are very interested about besides itself, robustness maybe bring us some generalization to the unknown data. Now, this talk will cover two papers. The first one is towards adversarially robust deep image denoising, and the second one is on the robustness of neural ODE models. First, let me give some brief introduction of the adversarial robustness. Suppose we have a deep neural network denoted by f theta, then it map an input x to a target, so its performance can be measured by a certain task-related distance, the distance between fx and y. So we can train the model with some data set, and after training, it can perform very well on the data set. But in real application, the observation of some signal always contains some uncertain noise. Suppose the noise is denoted by delta, and the strength of the noise is bounded by some constant rho. And a reliable model should maintain a very small distance between the put of the data and the original one. If the difference is very large, then we can say the model is not robust. But in the real world, we do not know the statistics or some mathematical property of the noise. So we need to consider the worst case perturb that is added to the original signal. And the worst case perturb can be defined by the optimization algorithm, optimization problem, which we want to find some perturbed version of X in the neighborhood of X, which maximize the difference between the original output and the current output. So this kind of if we measure, or if we measure the performance of the original network on this perturbed data, then the performance can be used to characterize the adversarial robustness. So how can we evaluate the adversarial robustness? Of course, we need to solve or approximately solve the optimization problem. And we can use some gradient-based method like FGSM or PGD-based method. And if the model involves some random modules, we also can use the expectation over transformation techniques to approximately solve the attack problem. So on different tasks, the robustness metric will be different. For example, on the classification, and we can use the classification accuracy on the perturbed data as the metric for robustness. On some restoration tasks like denoising or the super resolution, we can use the reconstruction quality on the perturbed data as the metric. Here, PSNR is a very common used metric to measure the reconstruction quality. So current research works have shown us that DNs are very vulnerable against adversarial attack. So how can we robustify the deep neural networks? The very common strategy is adversarial training, which different from the normal training. The adversarial training is formulated as the minimax problem. It means that during training, we first need to construct the adversarial examples of the original data, and we try to minimize the distance on the adversarial examples. Then, besides the original version of adversarial training, and some other variants has been explored, such as the curriculum learning-based method called SAT, and some sample rewind-based method like Garrett. Garrett is the work done by Jinfeng and his team, right? So now we move to the first work towards adversarially robust deep image denoising. Here is the denoising task. The true image or the true signal is very clean, but actually, if we use a camera or if we download some image from the internet, it always contains some noise. And so the denoiser tried to remove the noise and reconstruct the original clean image. So here, the following image is an example. Here we use X to denote the clean image, and suppose a sample from some distribution P. And the noise, we use V to denote it, and suppose a sample from the distribution Q. And usually we assume that the noise, the strength of the noise is limited, and we use the L2 norm over the distribution over the dimension M, and it is bounded by some gamma square, and it means that the strength of noise is bounded. And we also assume that the noise is zero mean, because if we add some constant to the image, it just in the grayscale image, it just changed the brightness, and it may maybe not induce some visually artifacts. So when we say something, some image is very noisy, it usually represents the visual artifacts. So here, the committee also assumed the noise or the mean of the noise is equals 0. And suppose we have some training data set S, and we can train the denoiser on this data set. And after training, the F theta gamma can deal with a noise sample from Q. But in real application, the status of the true noise may be slightly deviated from the Q. So in this case, how will the obtained denoiser F theta perform on the true noise? So if the performance is bad, how can we robustify the DIDs? So in the following of this paper, we will discuss these two questions. The first question is, how can we evaluate the robustness of the denoiser? So we consider the worst case perturbation. Here, X denotes the clean image, and Y is the common noise. For example, when we add some Gaussian noise to the clean image and use them for training, of course, after training, F theta can deal with Y. But here we are interested about the perturbation. So we try to find some perturbation data is added to the common noisy image Y, then it will maximize, means it will degrade the restoration quality, and it satisfies two constraints. The first one is the mean zero mean constraint. The second one is the perturbation strength. It should be bounded by some perturbation budget epsilon. So the left picture illustrates the problem, and the XY is a common noisy image, and we want to find the perturbation based on Y. And to solve this problem, we propose to use an PGD-based method to solve this optimization problem. So in PGD-based method, the most critical step is to map the current optimization variables onto the feasible region, which is defined by the joint of the constraints A and B. But it is very hard to directly write the form of the projection. So here we propose a two-step projection, means that we first project delta onto A is the zero mean plane. Then we scale the projection so that the norm of the perturbation will be bounded by the epsilon. Here, a natural question is that why cannot we use perturbation of delta onto B first, then A? Actually, here to answer this question, and we prove a very short theorem, and to show that the projection onto A then to B, this two-step projection is exactly equivalent to the projection onto the joint of A and B, and this can be formulated as the convex optimization problem, and of course the solution is quite simple. And here we told that the two-step projection is equivalent to the true projection, but if we switch the order of A and B, then it will not be equal. So now we have the attack algorithm. We can use the ops attack method to evaluate the robustness of deep image denoiser. Now, suppose we have a normally trained denoiser, means the denoiser is trained on common noise like Gaussian noise. And we have some ground truth image X, and its Gaussian noisy version Y. And we can see that the column C, the result of the denoiser to remove noise from Y, then the result image is quite clean. But if we use ops attack to construct the perturbation and add that to the Y, then we use the F theta to remove noise of Y plus delta, then the result is not good. And the picture is quite small. We can see this picture, and you can see on the right side, and some artifacts on the roof and in the sky. So of course here we also show some numerical results, and the values means the PSNR. The higher PSNR means the better reconstruction quality, and we evaluate the denoising performance on a very common benchmark dataset set 68, and for the gamma means we evaluate the denoising performance in terms of different level of noise. In each level of noise, we can see that the denoiser can effectively reconstruct an image from Gaussian noise and uniform noise, means the PSNR is quite high, around 29. But if we add some adversarial noise into the image, the performance degraded quite a lot. We can see that the PSNR dropped to 24 or 23. So now we know that the normally trained denoisers is not robust, and it's quite vulnerable against adversarial attacks. So how can we robustify it? So we propose a training strategy called hybrid adversarial training, and it's quite simple. It only contains two terms. The first one is nothing but the original training loss and the difference between clean image X and the reconstruction F theta Y. So the second term is the local smooth, means that the reconstruction of the common noise and the reconstruction of the adversarial noise image should be quite close. So here alpha balance the trade-off between these two terms, and if alpha equals 0, it's nothing but the normal training. But if the alpha be very large, then the optimization gradually ignores the first term, and we have a trivial solution is that F theta Y will maps Y to or 0, yeah, then the training loss will be very low, but it is not what we want. So in practice, we should choose a proper value alpha, and based on our study, and alpha usually can be 2 or 5, it will be okay. Yeah, here is some visual results, and we normally train to obtain and commonly denoiser to remove common noise like Gaussian, and we also use the hybrid HAT to train a denoiser. And here is the A is a ground truth, and when we deal with the adversarial noisy image, the normally trained one will show us some artifacts in the sky, but the HAT trained ones, the reconstruction image is quite clean. Here are also some numerical results. And VAT is another bench or baseline method, not the HAT is our proposed. And we can see that after training, when we deal with some common noise like Gaussian noise, the performance of HAT is quite close to the normally trained one. But when we deal with the adversarial noise, and the performance gap will be very large, and say when the noisy level is 25 over 255, and the attack level is 2 over 255, 3 over 255, then the HAT ones is 27.5, but the natural one is 26. Yeah. Then usually for a fair comparison, we make sure that the total noisy strengths in common noise and in the adversarial noise will be close. For example, what we do is that, say if we set the noise level to be 25 over 255, then we directly sample the Gaussian noise from and add that into the common noise one. But when we construct the adversary noise, we first sample a Gaussian noise with a lower strength, like 20 over 255. Then we add the adversarial perturbation into them, so that we can show that the total noisy strength will be similar. So now we propose ops attack to evaluate the robustness and propose the HAT to robustify the model. And so besides the robustness itself, what can the robustification bring us? So here we surprisingly find that adversarial robustness benefits the generalization to unseen noise. It means that in the real world application, we capture noise, or we capture image with a camera or with other devices, and the status of the noise is unknown. And many people show that the denoiser trained on common noise can barely deal with this unseen type of real world noise. But an existing method to solve this problem, even unsupervised one, they usually requires many image pairs, and such as noisy clean pairs or multi-view noisy pairs. But in some applications, especially the high-stake applications, it's maybe not possible to obtain these pairs. Now we show that HAT trained denoisers, only with synthesized noise, we do not need the real noisy image, and then the obtained denoisers can effectively remove the real-world unseen type of noise. Here's the visual result, but the patch is quite small, so maybe you cannot see the difference. And you can see the last row. Maybe you can see that the A is a noisy one, and some baseline including B, C, D, E, F, and you still can see some RGB colorful noise in the patch. But in the G column and HAT one it is very clean, very close to the ground truth one. Yeah. Zoom in, you can see that. So I'm sorry. So here is also some numerical results, and PolyU, CC, and SIDD are all real-world noisy image dataset. And we compare the HAT, our obtained method denoiser, with a normally trained one and with some other baseline method. We can see that here H2C means noisy to clean, means suppose we have the noisy clean pairs, then we can use the noisy clean pairs to train the model, and we use it at the upper bound of the method. And we can see that on the SIDD dataset, our method only used a synthesized common noise image, and the performance is very close to the N2C one. Yeah. So during application, and now you can you only need some randomly collect from internet. You can have some clear image, then you add some Gaussian noise into it and use the adversarial strategy to train the model. So after adversarial training, you can use this denoiser to most kind of scenarios. Yeah. So here is a simple understanding of why the robust benefits the adaptation to unseen noise. Because during adversarial training, the HAT first sampled the noise from common distributions like Gaussian, and the ops attack then explored the absolute neighborhood for each noisy image to search for a particular type of noise that degrades the denoising most. Then by ensuring, because we ensure the performance on the worst case, by ensuring the worst case performance, the resultant denoiser can deal with some unseen type of noise within the absolute neighborhood. Yeah, so here's a short summary of this work. This work systemically studied the adversarial robustness of deep image denoiser. First, we propose ops attack to evaluate the DID's robustness. Then we propose HAT to robustify DIDs. Finally, we uncovered that the robustness of DIDs benefits their generalization capability on unseen real-world noise. Yeah, this is the first work. Then we move to the second work on the robustness of neural ordinary differential equations. In the previous work, we study the robustness of, and we try to robustify the model from training strategy, the perspective of training strategy. Now, we also know that the model architecture is very critical part to robustness deep learning. So in this paper, we study the robustness property of novel model family NeuroOD. NeuroOD is quite novel in 2020. Now, yeah, it has been explored for 2 and 3 years. So let me briefly introduce the NeuroOD models. So suppose we have an ordinary differential equation, and Z is the state, Z is the d-dimensional state, and the derivatives or the dynamics of Z is defined by some function f. Then f takes input the state Z and T. This is classically a time variant dynamic system. And we denote the Z initial state Z0 as the input and the terminal state evaluated at T as the output. So if we fix T, then the output is the terminal state, and the relation between terminal state and the initial state is defined by this integral, the integral of f from time t to time 0 to time t, and this is also called the flow function. And the NeuroOD parameterize the dynamics f theta, and then we have a fixed t, and we have a fixed parameters of the dynamics. Then the relation from the map from input Z to the output is fixed. So this is NeuroOD. In practice, the number of t doesn't matter. We just set the t equals 0, and we can use various ODE solvers like Aura or some adaptive solvers to compute it out. And the NeuroOD has some very nice properties, like it is invertible, and the non-intersection between the evolution trajectory. This introduced some regularization on the trajectories between different inputs. So intuitively, we think maybe it will regularize the output of some perturbation of certain input. So it may be related to the robustness. Now we perform an empirical study of the robustness of NeuroOD. Means that we study the robustness of the by comparing the performance of ODNS and the CN. CN here is a residue, and the right picture, the picture on the right side is the total framework of the network. We use say we have 3 modules. The first one is a feature extractor, which map the input into a high dimensional feature space. Then we use a representation mapping, which is a dimension preserving mapping, because NeuroOD is the time dynamic system. The dimension of the state didn't change. So then the output of NeuroD will send to the fully connected classifier to make prediction. We construct the ODE-ness and the CN-ness based on this framework. And for a fair comparison, we make sure that ODE-ness and the CN-ness have similar number of parameters and use the same training strategy. The difference is that in the ODE-ness, the rep module is constructed by the NeuroD layer, but the CN is constructed by the residual layer. We evaluate the performance of ODE-ness and CN on different data sets, including MNIST, SVHN, and the image, because at that time, to 2020, when training NeuroD is very expensive, computationally expensive, so we collect a subset of ImageNet, and we train the model with Gaussian noise augmentation and to make sure that, and we also make sure that the classification accuracy on the clean data of different models to be close, to be similar. And we evaluate the classifiers against different kind of perturbation, including the very simple friendly Gaussian noise and of course the adversarial attack. So say, for example, on the SVHN dataset, the CN after training, it can the performance of the classification accuracy on the Gaussian noisy image will drop to 19, but the ODE-net will maintain around 95, especially when dealing with the adversarial attack, for example, FGSM 8/255, and the performance of CN dropped to 12.3, and the ODE-net is around 34. So here is a bunch of results, and it shows that ODE-nets are usually more robust than CN. Here, the natural question is why it may be more robust than CN. And here we provide an intuitive understanding or explanation for the 1D and 2D case, but for the high dimensional and higher than 3D case, it is still an open question, but we still can get some insights from the 1D and 2D case. Here's a classical theorem, short for the ODE integral curves never intersect. It means that if the suppose V is governed by the dynamics f theta, and f theta is continuous in T, and globally Lipschitz is continuous, so we can see that we will know that Z1 and Z2, if there are two different solutions of the ODE, then at any time they will not be equal, means the two curves will not intersect with each other. So why this kind of theorem may induce a better robustness property of NeuroD? So here we can see the following picture as an example. Suppose we have the robustness of the model is measured by the difference of output for the output of the perturbed input. So we suppose originally have the three input output pairs, and A1, A2, and A3, and after training, the NeuroD can map the A1, A2 to their terminal state. Now we are consider the perturbation of A1, the dot line, and tilde A1 is a perturbation of A1. We know that this theorem tells us that the integral curves never intersect. It means that the dot line always sandwiched by the blue line and the red line. So even at the terminal time t 1.0, and the output, the terminal state of tilde A is still located between blue and dot, or between the green and the blue. So it means that A tilde A is the perturbation of the A. Then in this picture, we know that the output of tilde A, the difference between tilde A, output tilde A, and A1 is always bounded by either the difference between green and blue or the blue and red. So it will not arbitrarily jump to some value and very far away from a blue one. So it means that the output of the perturbation is bounded in certain level. So it may tell us that this is why the robustness of NeuroD is better than the CN. So now NeuroD layers is a better module than CN in terms of the robustness. So we want to explore whether we can further improve the robustness of the NeuroD. Of course, we propose the time environment stable NeuroD TISODE, and we introduced two more constraints or two more regardation on the evolution trajectory. The first one, we remove the time dependency of t, so the dynamics becomes time invariant ODE. Means that f is only dependent on the state value. Now then we have a time invariant property TIV got p, and it means that suppose we have the evolution trajectory, the red line z1, and its perturbation version tilde z1, and it's the tilde z1, the initial state of tilde z1 is equals to the state of z1 evaluated at t prime. Then we know that the blue line is nothing but the horizontal translation of the of the red one. Then we impose a weak steady state constraint to it, because the robustness of the model always decided by the local smoothness, means the difference between output of the perturbed input. So we work for some datum z1, and we are interested about a certain type of perturbations, a subset of perturbations of z1. How can we which data set? So we define a set M1. The M1 is a set of state and time pairs. Each element is collected from the whole trajectory of z1, and which pair? So we from time 0 to t, and we evaluate the state of z1 and check whether the distance between z1 t and the original z0 is smaller than epsilon. This is the perturbation budget. So if the distance between current state and the initial state is smaller than epsilon, so then we collect it and put it in the subset in the set M1. So each element in the M1, it will corresponding to a certain perturbation, the perturbed data of the original data. Yeah. So so now Z1 is suppose we consider the tilde Z1 whose initial value equals to the the Z1 at T prime. Then for this kind of perturbation, we know that the distance between the perturbation, the norm of the perturbation is smaller than epsilon, and this is what we are interested. And so now we are interested how large the difference between the output of tilde Z1 and the original data Z1. So it is nothing but the tilde Z1 evaluated at T and the Z1 evaluated at T. So based on the time invariant property, we know that the tilde Z1, the trajectory is nothing but the horizontal translation of the original Z1. So this value is the difference between the states evaluated at different times of the original trajectory Z1. And because Z1 is smaller than capital T, so it always bounded by the integral of the absolute value of dynamics and from integral from T to 2T. And for each pair in the set M1, the difference between the output always can be bounded by the right term. So we can use this right term as a regression term and add it to the training loss. And for each data, this is the regression for datum Z1. Then for each datum, we all have this term, and the difference is the input of the dynamics f theta. So we can add this regression term into the loss function and training it with, for example, the classifier, we can train it with the cross entropy model. And then after training, we show the performance and the robustness of the TisODE net and compare it with the original neural ODE ones and the CN ones. For example, on the MNIST data set, we can see that when dealing with the Gaussian noisy image, and the performance of the TisODE is slightly better than ODE. But when we deal with the adversarial attack method, the performance of TisODE is quite clearly better than the ODE net. And this kind of superiority is consistently can be observed on different data sets. And yeah, here, time event TisODE impose a steady state constraint on the evolution trajectory of the neural OD. And actually, this is the weak regularization of the stability, because we just calculate the integral of the dynamics from t to 2t. Actually, the strength, more stronger regularization of the stability is we should regularize the Jacobi of the f theta, and if the dynamic system turn to be stable around some point, then the trajectory around this point should have the largest eigenvalue should be negative. Then it is much stronger regularization or constraint to construct some fixed point. So in 2021 and 2022, there are several follow-up works. They propose a regularization to construct the fixed point in the feature space, and the follow-up works can achieve much more better robustness in comparison to TRFC. Yeah. So here is the summary of this work, and we empirically studied the robustness of neural ODs for the first time. Yeah, our studies revealed that the neural OD-based models are superior in terms of robustness compared to CM models. Then we explore how to further boost the robustness of neural OD and propose the time-invariant stable neural OD. Yeah, I think this is these are the two works. Yeah, we only spent around 36 minutes. And yeah, here's a summary of today's talk. So the topic of this talk is the adversarial robustness of diffusion algorithms. We are interested about two tasks. The first one is denoising task. The second one is a classification task. For the denoising task, we proposed a observation-based attack for robustness evaluation. And we show that the current deep image noises are vulnerable against adversarial attack. And then we propose a hybrid adversarial training HAT to robustify the deep image noises. And we also show that robust noises can effectively deal with some unseen type of real-world noise. For the classification task, we explore robust neural network architecture, and we compare the neural OD with the CN ones, and we find that neural OD-based networks tend to be more robust in comparison to CN-based ones. Then we further propose the TIOC to boost the robustness of running the neural ODs models. Yeah, that is all my talk today, and thank you everyone for your attention. And if you have some questions, please feel free to ask. Yeah, thank you.
Yeah, if you have a question, please ask.
May I have some questions?
Yeah.
Can you show the loss function for height, HAT, first of all?
Sure. This one, right?
Yeah.
Yeah.
Because the standard AT usually learn the min-max optimization, but here you use different strategy.
Oh, sorry. Actually, this is a minimax problem because I use the Y prime here, and when we construct the Y prime, we actually need to solve a inner max problem. Yeah, because Y is solved by the attack problem.
Okay.
So yeah, because if I write the argmax into the object function, it will be too long. So I just use the Y prime here.
Okay.
Yeah.
Okay. So it's the same strategy as the standard AT.
Yeah, quite similar. Yeah, just the loss function have another term. I also tried to directly use F theta Y prime and X, and the performance is a little bit worse. Yeah. Then actually we do not know why, and this is kind of heuristic things. We need to explore different combination. And for example, the vanilla HAT and the trace and other type of adversarial noise, they study different kind of combination. We use the output with the ground truth or the output with the adversarial version. Yeah, we do not know why this kind of is better. Yeah.
Yeah. The small difference is here. If you use the standard, there should be the label of output Y X, but you use F Y. not
Yeah,
image.
yeah, exactly. The vanilla one is nothing but the difference between fy prime and x. Now we use two terms. First we encourage fy close to x, then we encourage the local smoothness.
Okay.
Yeah.
Also, another question about calculation. It seems you have two boundaries like zero mean and L2 norm. Is this equivalent to Gaussian distribution?
Equivalent to Gaussian distribution?
Yeah, because the Gaussian distribution seems similar to zero mean, and the L2 norm is some kind of verb.
Yeah, I think Gaussian distribution is one sub distribution of the distribution defined by these two constraints, right? Of course, Gaussian satisfy these two constraints, but I think other kind of, such as the uniform distribution, also satisfy this one, right? The uniform from -1 to +1, it also satisfy this one, right?
Okay.
So I think this is why we use the attack strategy to construct the perturbation, because we do not know which distribution is the best one to sample noise. So we just we just use attack method to find the worst case perturb. Yeah.
Makes sense.
Thank you. Thank you. I think I remember if we directly use fy prime and x, of course we can ensure the performance of fy prime, but my empirical results show that the performance on fy were not as good as this kind of thing. Here we explicitly use two terms, and the advantage is that we can make sure the performance on fy is good as well as the performance on fy prime. Yeah, I think. Thank you.
Yeah, I have a question
Yeah.
for your theorem here.
This one?
Yes. For example, right now you are using the L2 norm board. If you use L infinity norm board, would this theorem still hold? And perhaps not, right? For example, this is clear or something, not wrong.
I think if the two, because this one as well, as long as the constraint to be convex, then I think the conclusion will be consistent, because here actually it's not depends on the L2 norm, because the reason the theorem holds because it is a convex optimization problem. Then we can solve it and give a analytical solution to show that the projection is equivalent. And I think if we use infinity is just the box. Yes. Maybe box is still hold, I think. Yeah.
Right now we haven't explored this.
Yeah.
Because the real proof is only L2.
Yes. Yeah. The reason is that in classification tasks, maybe we usually use the L infinity norm. Then in the restoration task, the performance metric like Pearson or other things, it's usually based on the L2 norm. So here we just consider the L2 norm one. As okay.
I have a question in the paper where you discussed why the ODE is more robust than CNN. And you point out that it is theoretically because the ODE integral curves narrow that.
Yes.
And it is very interesting, but I'm not quite sure. Is it really true in higher dimensional? Because I remember, I'm not sure when we consider the three dimension, everything changed. Maybe
yes.
Not true.
Yes, exactly. Here the explanation only applies to the 1 dimension and 2 dimension. The higher dimension is there an open question, but the theorem shows that the curves never intersect. It holds for higher dimension. But yeah, but the in the high dimension case, the intersection, the never intersection property may not induce the better robustness. But in a low dimension, in 1D or 2D, we can show this demo and vision.
The curve
Yeah.
on the
Yes. In the 2D, it's just a circle and a larger circle and a smaller circle. Yeah. But in high dimension, I don't know. It's an open question.
Yes, because there is a lot of chaotic.
Yeah. Exactly. Yeah.
Can I ask a question?
Yeah. Sure.
Yeah. Thanks for the nice talk.
Thank you.
For those who are studying adversarial robustness, I'm always asking this question. But so once adversary knows what kind of attacks defense you are making, then they can somehow attack it easily, right? So this is more like an endless game. Once you propose a new defense method, then the next guy can rather easily find an attack method that breaks your defense.
Yeah.
So what's your opinions? Your paper, so you propose several nice methods, but in the near future, those methods will be broken by somebody else.
Yes.
What should you do?
Yes, exactly. Yeah, that is the dilemma, I think. Yeah, you have the spear and the shield. Yeah, you have attack, then you can defend it, and a more stronger attack, then you will break on your shield. So I think the second work on the robustness of TisODE, here we do not assume the certain types of the attack. So I think to explore more robust architecture, and it is a quite universal solution to build more robust deep networks. But if we study from the certain types of attack and certain types of defense training strategy, and this is a problem. And yeah, I think the answer may be that it should depend on the user's certain case. And for example, in the financial transaction or other high stake application, and the researchers should consider many types of attack and try their best to make the model can defend them. But in some applications for entertainment, like short video or the video communication, I think the attack even not so important. So I think this question should depend on the application scenarios. Yeah.
Yeah, I completely agree with you. So in a sense, the study of adversarial robustness is now into not really just a methodology research, but more on the system level research. So we need to consider particular application and also particular implementation system. Then we can somehow discuss the real robustness in practical scenarios.
Yes.
So maybe we should really jump into the next phase to boost this kind of research.
Yeah.
Okay, thank you very much. In particular, the latter half of the talk was quite interesting to me. Thanks a lot.
Thank you.
Yeah, all right. I feel no further questions. That's our today's seminar here. Thanks again for Han's quick updating.
Thank you.